This playlist deals with some aspects of Eurocoded 2 version 2023. Watch this playlist for further selected topics. This video will deal with clause 9, the serviceability limit state, and it's about minimum reinforcement to avoid yielding, part 2. In the previous video, we have seen the minimum reinforcement for tension and for bending, and now we will look at bending plus axial force. We are still in the case of minimum reinforcement to avoid yielding with the crack width not specified and the steel is yielding. The formulation as it is stated in formula 9.4 is as follows. In this formulation, you will see the term with 0.2 kH, and this is in fact the minimum reinforcement for pure bending. And you will see in this line the 0.5 kH, which is the minimum reinforcement for pure tension. So you will see that the minimum required reinforcement for bending and axial force, it's somewhere between the minimum reinforcement for pure bending and for pure tension. When you are in a hurry and you don't want to calculate all those kind of reinforcement, then you could know that you can use the minimum reinforcement for pure tension as an upper limit for bending and axial force. So that can be handy. In this formulation, you see NED. It is not clear what value of NED that should be. It's rather difficult to estimate this value. This is the minimum. This was the minimum reinforcement as the most tension side, and AS min W2 is at the least tension side, and it's just NED divided by the yield stress minus the minimum reinforcement at the most tensioned side. And the total must be smaller than AS minimum W1. So NED is defined as axial force at the serviceability limit state. But that's very difficult to estimate, because when NED, like a compression force, is put in this formula, it works positive on the minimum reinforcement. As from a certain value of NED, you will not need minimum reinforcement anymore. So it's an important value. So you should take the minimum of the compressive strength. But what is the minimum of NED? That's 0, isn't it? So it's sometimes difficult to estimate the value that you should take for NED. The tensile force is always positive, so the compressive force is negative. Now let's look at some more detailed. Suppose that NED is a tensile force. Then in this formulation, when you investigate that in more detail, you will see that the minimum reinforcement must be smaller than 0.5 times kH and so on, but must be bigger than this first point here. That it is positive, that's obvious. You cannot put negative reinforcement in it. But now you will see that you have a lower limit of AS min W1 and an upper limit. It does not say AS min W1 is equal to point in a formula. No, it should be between two limits. But which limit now has the priority? I will give you an example. Suppose that the tensile force is equal to FCT effective times the cross section of the cross section of the concrete. This is not far-fetched. It's NED equals to the cracking tensile force of the section. Now, when you put this value into the formula, it will lead to an absurd formulation, which means that AS min must be bigger than 0.46 times this, but must be smaller than 0.4 times 6, so which cannot be true. Now, what is the priority now? Which limit is a priority? If I put AS min smaller than 0.4, I will not comply with this limit, or vice versa. If I comply with this limit and I take AS min bigger than 0.46, I do not comply at this. So that's why there is something wrong with this formulation. Something is missing. And I propose that we should add the condition that the tensile force that you put in this formula must always be smaller than KH times FCT effective times AC. When doing so, you will not have those absurd evaluations like here. Second remark, when NED is a compression force, that means that NED is negative, but it's a little bit confusing to say that a negative force must be bigger or smaller than. So that's why I put the absolute value of NED is bigger than 2/3 KH times FCT effective times AC. If this is the case, then no minimum reinforcement is required. You can put it in more. You can also say NED must be smaller than minus 2/3 because it's a compression force, it's negative. So this is more correctly, but it can be confusing. So NED must be smaller than minus 2/3 than this. So we look at the general formulation, we plug in NED is minus 2/3 and so on. And then you will see that this first term gets 0. So AS min W1 is 0 because if you take those two limits again, then you see that AS minimum W1 must between 0 and this value. So if you can choose, why should you choose a value which is or less than 0.5 kh? So why should you take, for instance, 0.4 or 0.1? No, you take the minimum, which is 0, because you can. Because the only or the only condition here is that it should be positive and smaller than a certain value. So I take the minimum, which is 0. It complies. It complies with this formulation. There's no problem with that. So AS min is 0, and it means that AS min W2 is also 0 because it must be smaller than AS min W1 and positive. So both are 0. So as soon as you got a compressive force bigger than this value, in absolute value, then you do not need minimum reinforcement to avoid yielding. We can now play around with the formulation, and when you now make a graph, and on the x-axis it's nu, which is NED divided by FCK AC. For nu negative, it is compression. For nu positive, it is tension. And then on the other axis, we take the total reinforcement ratio. And the total reinforcement ratio is defined as the ratio for the most tensioned reinforcement plus the ratio of reinforcement for the least tensioned reinforcement. So rho is AS min W1 divided by BD, and rho accent is the AS minimum W2 divided by BD. To make a proper comparison, we assumed that G is equal to 0.9 times H. It doesn't matter, but it makes it a little bit more useful or easier to compare it in the graph. So it means that rho is defined as AS min W1 divided by AC divided by 0.9. This coefficient is just a factor, so it doesn't matter a lot for the conclusions that you can make. Now, the red curve here is the curve that of the graph that gives you the reinforcement ratio, the minimum reinforcement ratio at the most tension side, which is this one. And at the least tension side is the purple one. And the sum of the two is the blue one. So we see that at a certain point they come together and the minimum reinforcement is 0. The total minimum reinforcement is 0. When we can now look at slabs, we can make the same kind of exercise. For instance, it is done for a depth of 200 millimeters and a width of 1000 millimeters. We can make this exercise, and then you can, for this slab, you can now for each NED, again, I don't know how to estimate NED, then you can calculate the nu. You come here in the nu, and you can easily see what is the minimum reinforcement needed for what the minimum reinforcement is needed point. We have done that for different concrete qualities, starting from C30 up to C50 and from C50 up to C90. So all concrete qualities in between, for concrete between C12 and C50, you can, it's proportional. It goes from there to there, proportional according to this slope. And from high strength quality concrete, it's also proportional from this to this according to this slope. So it's always lines in between. So now you can draw for each section, you can draw an interaction diagram like this. You can draw it with row accent separately, or you can draw it for the total row. For beams, we make a similar exercise, but this time for a beam 600 millimeter depth and 300 millimeter width. This for C100, this is for C50, and this is for C30. Again, in between concrete qualities, you can make it by linear interpolation. And you will see you have a similar type of graph where there is a point where you don't need minimum reinforcement. We can now look at the minimum reinforcement to avoid yielding at the point where NED is bigger or equal to 2/3 kH FCT effective AC. We can look at that point and we call this V0. It's a non-dimensional compressive force. And we put it into a graph where on the bottom line, or on the x-axis, sorry, it's the minimum of the cross-sectional dimensions, width and depth. And on the y-axis, it is the non-dimensional compressive force that leads to no minimum reinforcement. And you can do that for different concrete qualities, going from C16 up to C100. And you will see again that the point where you don't need minimum reinforcement, that varies with the concrete quality. It varies a lot. This is half of this one. So it means that, for instance, for a beam with a minimum width of, or a beam with a width of 300 and a depth of 600, for instance, and then you will see the difference between the C100 and the C16, that for high strength concrete, the point where you, the normal force where you don't need minimum reinforcement is half of that for a regular concrete like C30.